come to this last part of the talk, of review talk, and we will discuss Schottky junctions and Ohmic contacts, and we will see why it is important in the device. So, Schottky junction. Schottky junction refers to junction between a semiconductor and a metal. Junction between a metal and semiconductor. As we will see, the junction could be, this could be rectifying, it could be a rectifying contact, rectifying, or ohmic. It could be a rectifying contact like a normal diode, or it could be an ohmic contact. We will see more on it. As you can appreciate, this is important because it provides contact electrodes or metal contact to the semiconductor. So, it is important because of contact electrodes to a semiconductor device. Therefore, metal semiconductor junctions are important in device characteristics. So, let me briefly talk about this. So, it is a junction between a metal and a semiconductor. So, a semiconductor here and it is a junction. So, it could be in planar epitaxial growth, it could be a metal layer grown on a semiconductor. So, this is metal, or it could be, so this is, let us say, N substrate. You make a PN junction by diffusion. So, you do N plus diffusion here and then a metal, and you can have P plus. So, P plus diffusion. So, normally you see that in an N substrate you diffuse first P, and then near the contact you either have P plus or N plus at the contact. Why is this? We will see from the characteristics. So, let us see what do I mean by rectifying contacts and ohmic contacts. So, rectifying contact, as the name indicates, it refers to a contact which allows current to flow in one direction but blocks it in another direction as it is done in a diode. So, if I draw the IV characteristics, so this is voltage versus I, current for a device. So, if you take a diode, we know that the forward characteristic and the reverse characteristic, and then almost saturated, and finally of course it breaks down. So, this is a typical, a normal diode characteristic, normal semiconductor diode. PN diode, forward characteristic and reverse characteristic. We will see that when you make a Schottky junction, then the characteristic normally, of course it depends on what kind of, so it starts to go up a little earlier, and similarly at the breakdown also it tends to come down a little earlier. Why it happens, we will see. And what is an ohmic contact? So, as you can see, this is a rectifying contact because in the forward direction we have good amount of current, because if you see the real scales, these are in milliamperes, tens of milliamperes, and the reverse that we see is typically tens of microampere. So this is tens of microampere and this is tens of milliampere. Typical diode characteristic, which means the current easily flows in the forward direction beyond a certain voltage and it is inhibited in the reverse direction, or the current is very small, and this we call as rectifying contact or rectifying behavior characteristic. Now, an ohmic contact, as the name indicates, ohmic, which means it is resistive, basically resistive. So, ohmic contact, which means the current is proportional to the voltage. So, I is proportional to V, and therefore, we expect a linear curve. So, a linear irrespective of the direction. So, this is pure ohmic. So, ohmic. A ohmic device, if you take a resistor for example, it is an ohmic device, whether you take the resistor R here and pass current in this direction or in that direction, or alternatively if you apply a potential battery in this direction or the other way, it does not matter. The current behavior is the same on either side, hence the name ohmic. Whereas for a diode, it does matter. So, forward bias and reverse bias does matter. So, this corresponds to forward bias, just elementary recalling. So, if you take a PN diode, then this corresponds to the forward bias here, whereas if you reverse bias, the characteristic will be like this. This will be tens of volts here and this will be 1, 2, 3, 4 of that order, just a couple of volts. Typical numbers if I want to put, this may be 1 volt, this may be 2 volt. And if I want to put some typical numbers here, this could be 10, 20 or 50, 100. So, depends, 20, 40, 60, 80 volts, reverse volt. And as I have written, it's therefore, you can clearly see that the forward flow is very easy. A small voltage applied gives you tens of milliamperes. Here, even if you apply tens of voltages, tens of volts as reverse bias, your current is only tens of microamperes. Whereas for an ohmic contact, it is identical, it is the same. In fact, the scale would be same for an ohmic contact. It is not really a straight line as I have shown here. For this scale, the scale has to be identical for ohmic contact. In between, there are near ohmic. So, near ohmic contact, and they look like this. So, the curve, let me also put a dashed line along with it just to differentiate. Near ohmic contact. So, this is near ohmic, not exactly a straight line, but good flow of current is permitted in both directions, near ohmic. And we will see that by taking a Schottky junction, that is a junction between metal and semiconductor, it is possible to get a Schottky behavior. So, this is the Schottky characteristic, which has slightly smaller built-in potential here, or it is also possible to have a near ohmic contact. The other methods of getting near ohmic contact include N plus junctions or P plus junctions. These also behave like almost ohmic contacts. N plus semiconductor or P plus semiconductor. So, before I go to the Schottky junction itself characteristics, let us first see this N plus. How is the characteristic? Qualitatively we will see how is the characteristic of N plus and P plus, whether they behave like. Why am I interested? You can see that here there is a N plus and then to the metal. Similarly P plus and then to the metal. Same thing you will see in optoelectronic structures. Almost all devices will have the metal. Just before the metal there will be a P plus or N plus material, and then there will be a P or N. So, you will have a P to P plus and then P plus to N to the metal. Similarly, at the other end you will have N plus to the metal and N to N plus, because they form near ohmic, almost very good ohmic contacts. How do they form? We can see from the band diagram. So, from this diagram what I have tried to illustrate is what do we mean by Schottky junction and ohmic contact? What are the characteristics? How does it come? It is very easily understood, although qualitatively, from the band diagram, energy band diagram. So, that will be my next task. So, let us look at the band diagram of an N plus semiconductor, and exactly like that you can see P plus semiconductor. You can try yourself how it would look like, why N plus would behave like a near ohmic contact, and so N plus junction. Energy band diagram. So, before contact, this is a N semiconductor, whatever it could be N silicon, and you have an N plus silicon, so highly doped. So, every time we will not write ECEV, you know what we are referring to. So, this is N plus silicon, N plus standing for highly doped. There is nothing like a P plus, there is nothing like N minus. P plus standing for highly doped. There is nothing like N minus. N silicon, N plus silicon. What do we expect the band diagram to be when we link the two? Remember that this means there is plenty of electrons here. It is very simple to imagine plenty of water. This is also N type, so there is and few holes here, holes, electrons. So, you can see a carrier concentration difference. Water here is more, so water would start flowing here. Electron has a higher concentration there, so it will start migrating to this when a contact is made. This is before contact. So, before contact, when electrons flow to this side will become positive, which means lower potential energy, positive, or this side becomes negative, which means higher potential energy, and therefore lower potential energy means this would start coming down, and you know that the EF has to be equal. So, what we get is so. So this is the n plus contact, energy band diagram of the n plus contact. Some electrons have flown here because of carrier concentration difference, which has brought down the band here, and you have very easy to imagine in terms of water. See now, junction, if we apply a positive plus, so forward bias, an n plus junction, if we forward bias, which means this end is becoming more negative, which means higher potential energy, therefore this band will start pushing up. If you forward bias in this, it is difficult to say which is forward, which is reverse, but if you connect the battery in this fashion, then this will start going up, which means more of water can flow easily. If you lift this, electrons will flow easily in this direction. There is very little resistance, so water can flow easily in this direction. In other words, current can flow through the circuit very easily. So the conventional current outside is like this, the electron current inside the semiconductor is flowing like this. What about negative? If you, instead of this, if you apply reverse bias in this fashion, then this will go down further because you are applying positive to this end. So electron potential energy will be reduced, so the band will go down. So does not matter if this goes down, water will flow from here to here. If this goes up, water will flow from here to here. The main point to see is in both the places there are plenty of carriers. There are plenty of electrons here as well as here. In other words, whether you forward bias or reverse bias, the device characteristic, that is IV characteristic, is almost identical. Therefore, it is a near ohmic contact. There is very little difference. So that is why you make n plus junction. The smaller the resistive loss, the better it is, otherwise there will be potential drop across these junctions. What about P plus? Exactly like this, if you make P plus, you can do it yourself and see that this time you will talk in terms of whole currents. So this is P plus, so plenty of holes now, air bubbles. So if you make contact, then what will happen? If you make contact, these air bubbles will start coming here, which means this end becomes more positive. So this is going from here positive, and therefore this starts going up till you get, so you please make it yourself. So you will have till so the majority carrier in this case is hole, whereas majority carrier in this case is electron. But the current flows predominantly due to one type of carriers, predominantly due to one type of carriers. So same way you make this up, make this down, it does not matter. In either way, holes will flow from this side to that side or that side to this side, because there are no barriers and there are plenty of holes on both the sides, exactly like this, plenty of electrons on both the sides. Lifting little bit this side, that side does not make any difference, and therefore these are near ohmic contacts. Let us see the Schottky junction now. So if you have understood how to plot the band diagram, then most of the time, at least qualitatively, you can see what type of characteristic that you can expect. So in the devices, we always encounter P plus junctions, N plus junctions, and of course, to give external contact electrodes, to make contact to the contact electrodes, we need semiconductor metal junctions. So let's see the band diagram of a Schottky junction, energy band diagram of Schottky junction. A metal is characterized by a Fermi function, below which normally it could be due to two overlapping bands or it could be half filled band, but it is characterized by a Fermi level, Fermi function, below which there are plenty of electrons, or at 0K all electrons remain below this. So typical this work function here, okay, let me draw this line as the vacuum level, that is 0 eV. Which means this is 0. So typical work function here, metal work function phi m, E times phi m. This is the potential. Phi is normally used as a notation for potential. So E phi m is the metal work function. So this is E f of m, Fm, m for metal, Fermi energy for metal. So metal work function. Metal work function. Typically, so typical values, let's have some idea about typical numbers. So typical values approximately of the order approximately 4.4 eV for aluminum Al, approximately 5 eV for gold. Silver is also approximately same, 4.4 eV, 5 eV for gold and about 5.1 eV for, I think, approximately 5.1 eV or 5.7 eV for platinum, 5.7 eV for platinum. Typical numbers of E phi m, work function of metals. So this is for Ag also, aluminum and Ag approximately 4.4, 5 eV and 5.7 eV. For platinum. Let me draw a semiconductor here. So EC, EV and EF somewhere. If it is n-doped, then EF is here, and this energy is called the electron affinity, E chi. So E chi is the electron affinity. Sometimes people call chi as the electron affinity. So electron affinity. Electron affinity. And this is E phi s, the work function of the semiconductor, E phi s. Although normally we don't use work function of the semiconductor, but this is analogous to this, we have work function of semiconductor. Typical numbers for chi, of course, phi s depends on whether you are doping N doped or P doped or N plus and so on, but chi has typical numbers for E chi is approximately 4 eV for gallium arsenide, approximately 4.3 eV for indium phosphide, and even for silicon it is approximately 4 eV for silicon for Si, and about 4.1 eV for germanium. No space here, 4.1 eV for germanium. Typical numbers. So what you see is, in general, there are some materials, for example, indium arsenide, this has 4.9 eV, closer to metals. But in general what you see is chi is smaller compared to the metal work function. That is why I have shown this above this level in general, but there are some variations and we will see its implications. What are its implications? So when I want to form a metal semiconductor junction, let me take this diagram itself, metal semiconductor junction. So if I am forming a junction here, then this is the Fermi level, this is the Fermi level here, this is a N-type semiconductor, which means there are plenty of electrons here, plenty of electrons. Here electrons are up to this level, therefore electrons will pour into this. Electrons will migrate here because this is a metal, therefore there are large number of vacant states above. It is generally, as you know, metals comprise of overlapping bands, where you have bands overlapping. So this is the conduction band and this is the valence band. When they overlap, there are plenty of vacant states here. This is all filled, plenty of electrons, but there are also plenty of vacant states. Therefore electrons can freely move through the vacant states. This is overlapping bands. Or you could also have only half filled band, which also means the same. Half filled means what? This is all filled, this is one band, but this is completely full, which means these are all empty. The electrons can easily go to the empty state and move. With a small application of potential, they can immediately move. That is why the conductivity is very high. When you make a semiconductor and metal contact, this will come down here. What would be the resultant? How would the band diagram change? We can apply the same methods which we have seen for semiconductor. How to, when electrons migrate over here, this end will become positive and this will start coming down. So what will be the resultant band diagram? This is the metal. There was a discontinuity here. Please see, there was a discontinuity. This was E chi and this is E phi m. There was a discontinuity. So we have a discontinuity here. This is the same as this. So this is actually E phi b. This is called the Schottky barrier. We will see. And then because this has gone down, the band starts bending. Because of migration, you remember, this has, there is a potential energy variation like this here, and therefore the band starts bending. Till the two Fermi levels, oh, I have shown this a little bit more because the gap. So I have similarly here so this is my EV, EC and EF of the semiconductor. This is EFM. So this is all filled with electrons. So EFM. So we have simply added this, but remember there are plenty of electrons. It is as if a p plus and n junction. It's almost like p plus and n junction. So this side we do see this, and therefore there is a built-in potential here. What do you think this will be? V built in, Vb, or E times V built in. This barrier is called the Schottky barrier, E phi b. Please see, if this is Eg, then this will remain Eg. This is Eg. If this is some gap here far away from the junction, then the gap should be the same here. This is the barrier potential. When you have made the contact, there is a variation which has come because of charge migration, but there is a potential barrier here because there was a discontinuity. If I extend this up to this, you can see there is a discontinuity, and therefore this is the discontinuity that we have, and this discontinuity is called E phi b, is called the Schottky barrier, or phi b is called the Schottky barrier potential. So E phi b Schottky barrier. What will that be equal to? In terms of phi m and chi, it will be equal to E times phi m minus chi. So generally we see that because phi m is larger than chi, generally this Schottky barrier is a positive quantity. Typically, although it looks that it is theoretically, it looks that it is this much, in general there are other considerations which come into play, and Schottky barrier is generally of the order of 0.6 to 0.8 electron volt for silicon and N silicon and metals, N silicon plus metal, and is generally of the order of 0.7 to 0.9 electron volt for N gallium arsenide plus metal. Some idea about what kind of Schottky barriers we have, barrier heights we have. Theoretically it is this much, but generally it does not come out exactly that much, but at least it tells you that in general phi m is greater than chi, and therefore there is a barrier. So we have to see what is the implication of the barrier and how we can control the barrier and how we can get an ohmic contact out of this. Right now what is the contact this is? Please see, there are plenty of electrons here, but there is a barrier. So water cannot flow over, there is a barrier unless you forward bias this. Let me continue with that and try to see what happens if I forward bias and if I reverse bias. And then we will understand how to realize Schottky barriers which are nearly ohmic in nature. The barrier potential is approximately this, but there is an interesting concept which will come. We will forward bias this. Forward bias means this is a n type, so we apply to the n side, we are applying negative, which means the energy will go up. So this band will start going up and electrons will pour over as this starts going up. When I forward bias, the new level is here. Let me show it with slightly to distinguish. Let me draw. After forward biasing, the band looks like this. The upper one is after forward biasing. So what has happened? The band has been lifted, which means there were plenty of electrons here. The electrons, because we have lifted, the electrons are going over the barrier and pouring into this. In fact, these are called hot carriers because electrons of higher energy being injected into this side. So as you lift this, electrons go over a barrier. When electrons go over a barrier to another side, it is called thermionic emission. This process is called thermionic emission. Thermionic emission. We have studied thermionic emission where electrons are emitted from a heated filament. It's not necessarily it need to be emitted, it has to come out of a barrier. There is a potential barrier, jumping over a barrier is actually thermionic emission. Not necessarily you leave the material and go. So this is jumping over a barrier, hence the name thermionic emission. So if you forward bias this junction, current will flow through this junction. This is a metal semiconductor. So what we have in the conventional picture is this. So this is the metal and this is the semiconductor, and we have forward biased. There are very little holes here. Some minority carrier, some hole current will be there because when you raise this, there are very little holes. Some holes can migrate here and electron can come down from here because this is a pool of electrons. Metal is a pool of electrons. But primarily the current is predominantly due to electrons and due to thermionic emission. What will happen if we reverse bias? This will go down if we reverse bias. If it is not confusing, then let me try to show the reverse bias in the same diagram. So that was forward bias. The diagram is a little smaller, but what would happen? This was without bias, this was with forward bias. So if you apply now a reverse bias, which means we apply positive to this end, electrons will have lower energy, so the band will start coming down. So the band will now come like this. So let me show these with dotted line, just to distinguish. And similarly here, this will also come down, and the Fermi energy comes down. So the lower band, if you wish you could draw a separate diagram, but I want to show in the same diagram because you can see all of them simultaneously. So the electrons have come down further and therefore they cannot anymore jump over the barrier because there is a potential barrier. Remember that this axis is always energy. So there is a potential energy there, barrier, so they cannot jump. It has come down. So the electrons are here, plenty of electrons are here, but they cannot jump. And therefore the current will be restricted, current cannot move freely, but there is some current which will come in this case. One, because this has come down, whatever holes which were here, they would immediately move up. Air bubble, remember air bubble will go up because this has been brought down, so air bubble is pushing up. But more importantly, there is a new current which comes, which is called tunneling current. There are electrons here. Electrons, if they find, let us say there are some electrons here. If they find at the same energy there are vacant states or there are states, permissible states, then electron can tunnel through this barrier. Now this part I will zoom in and show you more clearly. I have zoomed in this part for reverse bias. So this is EC of the metal and this is E phi B. there are plenty of electrons. There are electrons here, it is a n-type material, but there are also vacant states. There are electrons, but there are also vacant states. Here there are plenty of electrons. If remember that this axis is energy. If I take a particular electron here, a particular electron, it has energy equal to this much. Let us say this energy is E1. At E1, if I go to the other side, there could be a vacant state. There could be a vacant state here because electrons are there, but electrons and there are vacant states here. So, sometime there could be vacant state here. At the same energy, there could be a vacant state, but there is a potential barrier where there are no allowed states. Allowed states are on this side. There are no allowed states here. But the electron, if it finds a state there, then there is a probability of electron tunneling to this side. So, this is called tunneling current. This is tunneling is a quantum mechanical concept. I am sure the basic tunneling all of you have studied at some stage or the other. But the important point to see is if you have a potential well, let us say there are electron states which are permitted here, and this is the well and this is the barrier. So, this part is the barrier, let us say D is the barrier width, and L is the well width of the well. If you have a lower potential here, which means at this value of energy, if that can exist here, then this has a probability of tunneling into that region. It is, of course, please see, let me draw this very carefully. You have an evanescent tail here. This is the solution which has an evanescent tail which is outside the well, because it is a finite well. A finite well has an evanescent tail, and when it reaches here, oscillatory solutions are permitted. And this means the electron can exist here. It can exist here, it can exist here, because there is a evanescent tail here. It is exactly, those of you who have studied optical waveguides, it is exactly the same. You have N1, you have N2, there is a wave, the fundamental mode looks like this, oscillatory solution inside and exponentially decaying solution here. If I now bring in a medium, so this was N2, if I now bring in a medium of refractive index N1 here, then it can have the same oscillatory solution here as well, and therefore immediately this starts oscillating, which means the wave can, oscillatory solution means it is a propagating solution. So, you can have the wave in this region as well. You can have energy coming into this region, and this is called tunneling. This phenomenon is originally quantum mechanical phenomenon, but it can be very easily illustrated in light experiments. All the prism coupling experiments and directional couplers work on this method. So, let us not go so much into this. The important point is, if there is a barrier, then tunneling is possible, but the tunneling probability is proportional to, inversely proportional to the width of the barrier. Smaller the width, larger is the tunneling probability. This is a quantum mechanical result which you can show. Smaller the barrier width, larger is the tunneling probability. And if you look at this, therefore, in reverse bias, the current is primarily due to tunneling. If I want to increase this, right now tunneling probability is very low because the barrier width is very large. If I can somehow reduce the barrier width, I have a very large probability of tunneling, and therefore I can increase the reverse current. So, how can I reduce the barrier width? So, if I could somehow reduce the barrier width like this, for example, then tunneling probability would be much more because barrier width is much smaller. So, I can have a much larger reverse current if I could reduce the tunneling probability, if I reduce the barrier width. How to reduce the barrier width? By doping this semiconductor heavily. If you dope this semiconductor heavily, then the barrier width will be reduced. How? So, let me draw the energy band diagram corresponding to the metal and a highly doped semiconductor right here. And then we see that the forward current is through. So, we have the metal, this is the barrier. So, we had the semiconductor highly doped, and here is the EFM of the metal, and EF of the semiconductor. So, this is EC, this is EF of the semiconductor, EV of the semiconductor. So, as soon as the contact is made, the Fermi level has to be aligned. So, electrons from here, the electrons from here go over the barrier and get poured into, there was no barrier, electrons get poured into this side, and this band starts coming down. Because it is N doped, it is N plus doped. This is aligned now. There are plenty of electrons here. If you wish, you can erase or you can draw a separate diagram. Because it was N plus, it had large number of electrons right here at this junction. So, at the junction region, the electrons are primarily have gone from the junction region, and therefore, this end has become more positive, and you see the barrier has now changed into. So, this is the new band diagram. What I have illustrated is, now you see that in this case the barrier width is very small. Therefore, if I apply a small potential, a forward potential like this to this, then of course this will get lifted and electrons can subsequently jump over the barrier, but also electrons from this direction can also tunnel because the barrier width is very small. If I forward bias, this will be raised and subsequently electrons can get poured into this side. It is like water, you are raising this, water is getting poured, but also because the barrier width is very small, tunneling can take place to this side. There are plenty of vacant states, these are all vacant states on this side. This is filled states, plenty of electrons. So, you can have electrons tunneling in this direction. So, the forward current IF will comprise of thermionic emission plus tunneling, plus tunneling. Plus tunneling. If you reverse bias this, then now you reverse bias, which means to this side, this is N side, therefore to this side you apply positive. So, this band will come down further. So, let me draw in the same diagram. There is a difference in the Fermi levels now. EF has separated out. So, this is reverse biasing. What do you see? There is a small plenty of electrons here, and there are electrons and states here, and current can tunnel through this very easily because the width of the barrier is very small. And therefore, even in the reverse direction, current can flow across the junction but the reverse current is primarily due to tunneling, whereas the forward bias it is due to thermionic emission plus tunneling. So, the reverse current IR will be primarily due to tunneling. Therefore, now if you plot the IV characteristic, in the forward direction also current flows almost freely, in the reverse direction also current flows almost freely, and the characteristic that you would get is a little bent, of course. Here it is not like an ideal ohmic, but so this is a near ohmic contact. I have tried to explain an N plus and semiconductor junction. You could as well have a P plus and a semiconductor junction. You do need a P plus because a device has PN junction or a PN device, you will have to make metal contacts to N plus also, but also to P side, and therefore there are similarly P plus devices P plus metal semiconductors can also be realized. I will stop here, and it would be a good exercise to see. I have discussed the case where phi m was greater than phi s. That is, this difference here was larger compared to the difference to phi s, which is up to the Fermi level, because you remember I started with the metal sitting here and EC sitting here, and there was a positive barrier. Suppose this was phi m, E phi m to the vacuum level, and this is E phi c. Suppose this level was below. This is a case where you have aluminum which is 4.4 and indium arsenide which is 4.9. Chi for indium arsenide is 4. So, this will come down here. This is EC for indium arsenide. This will be a very interesting problem to see. What type of junction will you get? If you have EC of indium arsenide here and aluminum here, so this difference is 4.4 electron volts, and this is the vacuum level 0. So, this difference is 4.9 eV. So, 4.4 eV. What do you think will it be? Find out what it is going to be, and you will see that there is no Schottky barrier in this junction, and it will be a very good ohmic contact. Current can flow freely in both the directions, and but we do not have many metals and semiconductors where you can have this situation where phi m is smaller than chi. So, if phi m is smaller than chi, then there will be no Schottky barrier. All right. So, we take a quiz today. I have already told you what will be the quiz. So, it should not take much time for you. The energy band diagram of the materials that make the emitter, base and collector of a NPN heterostructure transistor are shown below. There are heterostructure transistors exactly like double heterostructures that we have in optoelectronics. So, N gallium arsenide, P gallium arsenide and N aluminum gallium arsenide. The energy band diagram individually before contact is shown. Draw the energy band diagram of the NPN device. That is when it is connected. When the device is formed. So, this is the energy band diagram of the individual materials. N gallium arsenide, P gallium arsenide and N aluminum gallium arsenide. Draw the energy band diagram of the without any bias. When there is no external bias, what is the energy band diagram of the NPN device?